Example 7.2. 2-point sources emit in-phase light waves with wavelength lambda. Waves 1 to reach point P on the screen at location YP. A. Conceptually explain each situation. At what value of YP do the rays have the minimum and maximum possible phase difference? B. How many constructive and destructive interference fringes are there? Sketch the interference pattern that includes path differences delta R, MC, and MD values. C. Calculate the phase difference when YP is equal to 6 lambda. Is the resulting intensity maximum, minimum, or intermediate? That is it closer to a maximum or a minimum? We want to understand what type of interference occurs at point P. So let's define some variables for clarity. So if I move this up, I'm gonna put in this guy right here. So I'm gonna reduce this a little bit. And what do I see here? Well, I see ray 2. So I'm gonna say that takes a path 2. This is not a ray, this is a wave. I misspoke. And this wave takes path R1. And when you look at that, look at the two sources here. So the two sources, that is 1 and 2, are separated by the path difference. So let's define delta R, which is the path difference. And this situation has to be 6 lambda. So right away, we could come over here and just say, yep, there's my path difference right there. So when I look at the screen, we could see here that source 1 distance to screen is, of course, you could see that that distance is what? That is 20 lambda. And if I look at source 2 distance to screen, you could see that that has to be 20 plus 6. So this is going to be 26 lambda. And then our phase, that tells us that the phase is equal to 2 pi lambda delta R. And delta R is the important piece here, because it's path difference that determines type of interference. So we're always interested in delta R, but just to be as clear as possible, this is the path difference between 1 and 2. Okay, so now that I've defined that, let's go back and start answering the question that we started with now. So we want to know what is the minimum possible and maximum possible phase difference. So let's start off with the minimum phase. The minimum possible phase. It's really phase difference, but I'm writing phase. Okay. So then the question is, when does this occur, right? Maybe I should be a little bit, when does this minimum occur? Well, the smallest possible phase is 0. That's the smallest possible phase. So what that means here is that if I'm looking at the minimum possible phase, and I know that that's 0, then what it tells me about the phase equation is that the path difference has to be that minimum. So clearly in this situation, delta R minimum is equal to 0, implies that R1 and R2 have to have the same distance. So what this is really telling us is that this is only true if both waves travel the same distance to point P. But when you look at that picture, you're going like, how could they do that? The only way they're going to do that is if you take the limit to infinity. So this occurs as P approaches infinity. So that means that mathematically, what we're saying here is that in the limit as R1 and R2 approach infinity, then delta R goes exactly to 0. That's the only way that could be true. So how do I sketch this thing? So what I'm going to do, let me draw my screen. And let's say that here's my screen right here. And what I'm seeing here is that I have two sources. I have a source right here, which is source 1. I have a source right here, which is source 2. And now what I'm going to do here is that I'm going to let y of p approach infinity, where this point right here is infinite right here. So this is my point P right there. So if this is infinitely far away, then the path that these guys go from here to here, they start to approach the same length, right? These guys approach the same length right there. That's what that picture is really telling us here. And what you're going to see here is that because the phase at this location right here then, so at this location right here, the phase, the minimum phase is equal to 0, but that's no phase, so that means here I get a bright fringe right there. So let's put this together now. So the minimum phase is 0 located at yp equals to infinity. Here, there is a constructive interference location. So conceptually, this is what we would have. Now let's go to the other possibility. The other possibility is that we're looking at the maximal possible phase. So we asked the same questions that we asked before. When does the maximal occur? In other words, what is the maximal possible value for the phase difference? So from our phase equation, we know that the maximal has to occur when the path difference is maximal. So this really now tells us, where does delta R maximal occur? Really, that's how I'm doing that. And what you're seeing here is that if you look at it picture-wise, here's what we see. So picture-wise, if I look at my screen, right, I'm looking at my screen here, and now I have my two sources. Here's my source 1, and then here's my source 2. So if I have angles, then the path difference is not maximal. The only time we get maximal is when y of p is 0. So the largest path difference occurs at yp equal to 0. So that means here is that if I look at this distance right here, right, the distance from here to here, that is, of course, R1. And then I have this distance from here to here, which is R2. So you could see here is that the maximal distance is then going to be the path difference delta R right there. So what I'm really saying here is that delta R max at yp equal to 0, and remember this is yp equal to 0, that's got to be R2 minus R1, but remember how we defined R2. R2 was 26, R1 was 20, but we already defined what our delta R was, and we said up here that that was 6 lambda. So this path difference here is 6 lambda, which then tells me that the largest possible phase here is then going to be 2 pi lambda times 6 pi, which then gives me 12 pi, and that's the largest possible phase right there. So if I was to summarize what we just said here, it says that the maximum phase in this case is 12 pi. Located at yp equals to 0. So here, so this is a constructive interference location, since it's 6 wave path difference, which is an even number of waves here. So now we could go in and start calculating what we need to calculate here. So now we're on B. And on B, what we're going to do here is that we want to ask the question, how many constructive / destructive interference fringes are there? So here's what we know. From part A, we saw here is that there was a range for the phase, right? There's a minimum and there's a maximum. So we saw that this guy was 0, and then this one was 12 pi, but I'm going to write this as 6 times 2 pi. And so what that really tells us here is that right here, what we've done here is that we have identified MC. So that 6 is our MC value. That tells us that we have the following. So what this tells us here is that we know that the path difference is MC lambda guarantees constructive interference. So in this case, this is really what? I get 0, 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, and finally 6 lambda. So here's what I think is really interesting. This occurs at yp equals to infinity. This occurs at yp equal to 0. So this tells me the number of fringes that are between 0 and infinity here. So that is that the number of bright fringes between 0, yp, and infinity is 7. So now let's draw a picture of this situation. Okay, so what I'm going to do here, I'm going to look to draw what I think the pattern's going to look like, and I'm going to draw it like this here. It's going to look something like this. So here's my screen, right? So here's my screen right here. And when I look at my screen here, I'm going to have my bright and I'm going to have my dark. So what I'm going to say here is that I'm going to try to draw it. So I got 1, 2, 3, 4, 5, 6, 7. So I got to draw in 7 bright fringes here. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Now I got to come in, I got to put in my darks. So in between each bright is a dark. So now I could start labeling these guys now. So look at the way I'm going to start labeling these guys. So here's my MC value. So this guy here is my 0th, and I have 1, 2, 3, 4, 5, 6. And when I look at my path difference, I then see what? I see that my path difference is 1. Here it's 1 wavelength, 2 wavelengths, 3, 4, 5, and 6. Now, if I look at so if I'm being really careful here, note that this here represents yp equal to 0, and this represents yp equal to infinity. Now let's do the darks here. So if I look at this thing, what do I see here? Here's my MD value. So MD value starts off at 0, then it goes 1, 2, 3, 4, and 5. And then associated with this is their path difference. So their path difference here should be half a wave, 3 halves, 5 halves, 7, 9, and finally 11 halves of a wave here. So to give you a better idea here, I'm going to try to draw this on the screen, but slightly different. So what I'm going to do here, I'm going to try to do this, and this one's going to be harder to draw. Let's see if I could match it up here. So what I need to do here is that I need to look at the intensity pattern. Okay, so I'm going to look at this intensity pattern, and let's see how I do here. So it's going to go 1, 2, 3, 4, 5, 6, 7. Oh, right. It actually worked out. So these are my intensity patterns. And what you're seeing here is that, again, you could see here, this is yp at infinity. So at yp at infinity, I have a constructive. At yp equal to 0, I have constructive. So now I can count them. So here we go. So let's count the number of fringes. So in this case, we could see here is that if we talk about constructive, I see here that this really tells me that I have MC equal to 0, 1, 2, all the way to 6 here. And that tells me that there are 7 bright fringes. And if I look at destructive, our picture shows that MD goes from 0 to 1 all the way to 5. And this tells us that there are 6 dark fringes. So we have now sketched the interference pattern along with the number of bright and dark fringes. So instead of going all the way back up, what I did here is that I'm just going to now come in here and put in part C. So now our job here is that we want to calculate the phase difference when yp is equal to 6. So let's go look at that. So what we're asking you, right? So immediately what we got to do here is that we're asking, what is the phase when the phase when yp equals to 6 lambda. So, okay, remember our phase equation says it's 2 pi lambda delta r. So this means here is that we must determine delta r. So what we'll do here is, to get a sense of this, let's draw a sketch here of the situation. Oops. I think I'm spelling this right. That is not right. So if I look at this thing, here's what we see here. I have a screen. Okay, here's my screen. And what I'm doing with my screen here is that I have 2 sources now. I have my orange source here, and which is going to go to some point here. So let's say that it goes to this location right here. So this is going to be R1. And then I have a second source that now interacts right here. And that's what we call R2. Now, this location right here is what we're saying here is yp equal to 6 lambda. So what this tells us here is that we know this distance right here, we know that's 20 lambda. And we also know this distance right here, which is 26 lambda. So what you're seeing here is that there are two triangles. And we need to calculate the lengths. So we need to calculate the lengths of those hypotenuses of those two triangles in order to determine what the path difference is. So what I'm going to do here is that I'm going to use Pythagorean theorem. I'm hoping that's spelled correctly. We're going to use Pythagorean theorem to determine the lengths R1 and R2. So let's go look at that. Look at the orange triangle. So if I look at the orange triangle, to get R1, then it's the sum of the sides, which will then be 20 lambda squared plus 6 lambda squared square rooted. So then this guy, of course, if I factor out the lambda square, this gives me 20.88 lambda. Now I'm going to do the exact same thing for R2. So if I look at R2, this here is 26 lambda squared plus 6 lambda squared square root. And we know that this value from a calculator is 26.68 lambda. So now I can get the difference between these. So the difference, delta R, is then going to be the difference between these two, which will then give me 5.80 lambda, and this is delta R. So this is a very important value, because now, here we go. So the phase between these two waves at this location, right? So the phase at yp equals to 6 lambda is now going to be, so the phase at yp equals to 6 lambda is then going to be 2 pi lambda delta r. So delta r is then 5.80 lambda. And here, it's super important that you don't combine the 2 pi with the 5.8. So what you do here is that you leave this out so that you have 2 pi times 5.80. This right here, this represents the M value for constructive interference. So to show you, so now to find the location of this thing, so now let's sketch to find the location. And what I'll do here, instead of redrawing this, I'm going to come right back up. I'm going to grab this guy right here. So if I grab this and I paste it down here and just slightly modify it, actually, we don't need to slightly modify it. We'll leave it just as is. What you're seeing here is that the M value is 5.80. is not an integer. So what that implies here is that it is not maximal constructive / destructive interference. In other words, it's an intermediate value. So now let's draw this out. So you could see that this guy is somewhere over somewhere like right down here, right? Somewhere around there is 5.80. So it's hard to actually see that. So what we should do here is that we should draw some peaks. So if I look at some peaks, let's look at a peak that goes like this. And so if these are some interference peaks, what I'm going to do here is that I'm going to label the last 6 or the last 3 peaks here that we see. So this guy's going to be 4, 5, and then right here, this is going to be 6. So what you're seeing here is 5.8 is closer to a maximum right here. Right? So this is 5.8. So this implies here is that it's closer to a maximum than a minimum.